So first of all, welcome to the lecture of the material science. Today we are going to talk about the crystal structure in chapter 3, and as usual, let's have a quick recall about what we have learned in the previous lectures. In the previous lectures, we learned we start from the metallic crystal structures, and then why we start from the metallic crystal structure. We don't talk about ceramic crystal structure or polymer crystal structure, because it's for the ceramic or polymer, the structure involve more than one atoms. Like you can have carbon, you can have hydrogen, you can have nitrogen, or you can have sodium, chlorine atoms, something like this. So it makes things more complicated. So that's why we first of all we focus on only one single type of atom. For example, you can use gold atoms to make a crystal structure, or you can have a silver atom to make a crystal structure, something like this. That's why we start from the simplest case, and to let you understand the crystal structure. Okay, so we start from the simple cubic structure. Okay, simple cubic structure is that you have 8 atoms in the 8 corners in a cube. So as you know that we have 8 atoms in the 8 corners, right? This is called simple cube. And the first term we want to understand, we want to know, is called coordination number. The coordination number is the definition of the coordination number is that how many atoms the atom touched, or the nearest atom. That's what we call coordination number. So for example, if we point this atom, and how many atoms nearby this atom is called coordination number. For example, this one, if we regard this one as this one here, and there are 6, 1, 2, 6, 1, 2, 3, 4, 5, 6. There are 6 atoms surrounding this atom in the center. So the coordination number is 6. That's what we know. Okay, this is the first term we want to know. The second term we want to know is called atomic packing factor. So the definition of atomic packing factor is the value of the atoms in a unit cell. As we know, this is called unit cell, divided by value of the unit cell. So you want to know what's the value occupied by atom in a unit cell. This is what we call atomic packing factor. Okay, for the case of the simple cubic structure, the atomic packing factor, we also use APF for short, and it's 0.52. That means what? That means there are only 50%, almost 50% occupied by atoms in a unit cell, which is not big. You only half of the space occupied by atoms. Not good, right? Right, and because this is not a good structure, so there are only one elements belong to this structure, which is polonium. Polonium here. This is the atom which use this structure to make a bulk material like this. Okay, and the second case is what we call body-centered cubic crystal structure. The body-centered cubic crystal structure is a little bit more complicated compared to the simple cubic structure. So body-centered cubic structure means that you have 8 atoms in the 8 corners, and you have 1 atom in the center. And this is what we call body-centered cubic crystal structure. Okay, and again, we also want to know the coordination number, and we also want to know the APF. But before we understand these two terms, understand these two, we need to know the relationship between the radius of the atom and the edge length of the unit cell. And this, according to this equation, we understand the length of the edge or edge length will be equal to 4r. R is the radius divided by root 3. Okay, because of this equation, I'm sure you all understand this. So for the body-centered cubic crystal, it's this. After we calculate, there are two atoms in this. There are two atoms in this unit cell, right? So the APF after we calculate is 0.68. So that means what? There are 68% of the space in this unit cell occupied by atoms. Okay? Right. So as you know that because this is the APF is higher than the APF of the body-centered cubic structure is higher than the simple cubic crystal structure. So you will know that there are more atoms there are more elements belong to this crystal structure, such as the atoms in the periodical table, number 1, number 5, number 6, number 1 here, number 5 here, number 6 here. So these are the atoms, the elements belong to of the crystal structure, belong to the crystal structure, or belong to the body-centered crystal structure. Right. So today we are going to talk about let me check. Sorry. Good. Okay, today we are going to talk about another crystal structure called face-centered cubic crystal structure. So what is the definition of how does face-centered cubic structure looks like? So this is the, you have, let's start from the beginning. You have 8 atoms in the 8 corner. And then you have 6 atoms in the face of this cube, in the 6 faces. So that's why if you use a reduced sphere model to represent this structure, it looks like this. You have 8 atoms in the 8 corners, and you have 6 atoms in the 6 faces. Okay, so this is what and this is half sphere crystal, half sphere unit cell model, right, of the unit cell. Okay. Right. So this is about face-centered cubic crystal structure, and this one represents, if you count from the layer here, this sphere or this atom represent this one. Okay. This is we call stack sequences. If you put a 1 here, and then in the bottom you can put another 6, 1, 2, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is layer 1. This is layer 2. And you have layer 3 in this one, and this one belong to this one, this one, this one, this one, this one belong to layer 3. Layer 3. So layer 3, you have light blue atoms packed in a layer 3 represent these atoms here. So this is what we call stack sequences. I'm going to talk about this more later. So let's have some information about face-centered cubic structure. So atoms located at what? At each of the corners. First one. Second one, in the center of all cube faces. Okay, there you have atoms in the center of all cube faces. 1, 2, 3. 1, 2, 3, 4, 5, 6 here. So this is called face-centered cubic phase crystal. So how many atoms in this unit cell? There are 4 atoms in each unit cell. Can you count this for me? Can you? As we know, you have atoms, 8 atoms in the 8 corners, right? So, and one atom has 1/8 of the value in this unit cell. Again, so you have 8 times 1/8. That means 1, right? Okay. And how many atoms for the rest? For in a one phase, half, right? Half. So you have 6 phases, and then you have half atoms in one phase. That means what? 6 times half, right? That means what? 3. So in total, you have 4 atoms in this unit cell. No problem, right? Okay. Right, and then in order to understand APF, we need to know the relationship between the cube edge length and the atomic radius. So you want to know the cube edge length related to the what? Atomic radius. So could you do this for me? Easy, right? Easy. Because the edge length is A, and you have 4 radius here. 4 radius. 4 radius. So easy, right? So A power 2 plus A power 2 equal to 4R power 2. As a result, you got A equal to 2R root 2 here. Any questions? No, right? Easy. Right, so what's the coordination number? Tell me what's the coordination number. Ladies and gentlemen, I want you to remember this in your mind, because I will have a question for you, and you need to know, you need to calculate APF for me. You need to calculate the relationship between radius and edge length for me. Okay, so what's the coordination number here? Let's take a look of this one. To start with the to start to calculate the coordination number. So you have 1 here, right? So how many in the same layer? How many atoms? 1, 2, 3, 4. So you have 4 here. This is layer 1. How about layer 2? Let how many atoms touch or nearby this atom? 1, 2, 3, and 4, right? There's another one behind this one. So layer 1, you have 4. Layer 2, behind layer 1, you have 4, right? So 4 plus 4. And then please don't forget, there's a 1 layer in the front of this layer 1. We can call layer 0, for example. So another another 4. 1, 2, 3, 4. So 4 plus 4 plus 4, how many? 12. So the coordination number is 12. So for the metal, each atom has the same numbers of the nearest neighbors or touching atoms, which is the coordination number. This is the definition of the coordination number. Nearest neighbors or touched atoms. For FCC, I just told you the coordination number is 12. Or I should write 4 plus 4 plus 4 because you have layer 1, layer 2, and layer 0. Yeah. Or you can say layer 1, layer 2, layer 3. Doesn't matter. Okay, so I just do it for you. For example, this layer 1, you have 1, 2, 3, 4, right? For the layer behind this layer, let's say layer 2, you have 1, 2, 3, 4, right? For the layer in front of the layer 1, the layer 1 is 0, layer 0, for example. It's 1, 2, 3, 4. Then you have 12. So how about APF? APF, let's write down the definition. The fraction of the solid sphere's value in a unit cell. This is called what we call APF. And as we know this, right? So as we know, how many atoms in this unit cell? 4, right? And then you can This is the value of the one sphere, one atom, and divided by the value of this cube. So the answer you got is 0.74. So as you know, for the FCC structure, you have the APF is 0.74. For the BCC, that will be 0.68. For the SC, you will have 0.52. So which one you like? I mean, which one is the highest packing? 0.72, right? Okay, so that means there 74% value was occupied by atoms in a unique cell. So this is FCC, SC, this is BCC, this is FCC. So 0.52, 0.68, and 0.74. So APF of FCC, which is the maximum packing possible. So for the atom, for the metal, FCC is the highest packing APF. So metal typically have relatively large atomic packing factors to maximize the shielding provided by free electron cloud. So 74% is very high. So we like this packing factor. We like this type of packing, I should say. So I hope you still remember I just told you stacking sequences. Stacking sequences is this. You know that this layer 1 is C layer. Layer 2 is B layer. Layer 1 is here, right? You represent the orange ball, blue ball, and green ball. So this is what we call packing sequences. We call A, B, C, A, B, C. This A layer, B layer, C layer, A layer, and then next one will be A layer, next one will be B layer, next one will be C layer. So A, B, C, A, B, C, A, B, C. Show you. So if you take a look of the two-dimensional projection, as you can see, this A site here, A represent as a blue balls here. Sorry, this is not blue, right? This is green. Okay. There's a green ball here, and then you have, and next for the next layer you have two choices. Choice 1 is B site. You put the ball in the B site. But once you put the ball in the B site, you cannot put the ball in the C site in the same layer. So you have two choices. First one, B site. Or you call B layer. Or you can put it as a C site. In the case of FCC, we put the ball in the B site. Atoms in the B site. Okay? And next one. Next, after you put a B layer, put the ball in the B layer. Next one, you have two choices again. You want to put the ball into the A site, or you want to put the ball in the C site. Again, if you put the ball in the A site, you cannot put the ball in the C site. Okay, so for the FCC, this it will be C site. So you put the ball in the C site. And I'm going to talk to you about packing sequences of HCP, hexagonal close pack. That will be ABAB. Packing sequences will be ABAB. I'm going to show you this very soon. Okay, so this is FCC stacking sequences. So as you know, this is the maximum packing possible. So there are many atoms, elements belong to this kind of packing type, FCC. So for example, the elements in the periodical table, group 2, group 9, group 10, group 11. So group 11 here, group 10 here, group 9 here, and then some of the the lead, okay, and calcium, magnesium, something like this. Okay? Right. So for the next case, it's called hexagonal close-packed crystal structure. The hexagonal close-packed crystal structure is that the unique cell of the hexagonal close-packed crystal structure is this. This is unique cell. Unique cell is what we call the minimum, the smallest size, and then this size you can repeat these unit cells for all directions. This is called unit cell. So there are two key points you need to remember. One is the smallest size, and second is you can repeat this smallest size in all the directions. Right. So for a hexagonal close-packed crystal, it looks like this. So you have what? You have 6, 1, 2, 3, 4, 5. So you have 6. I should say 12. You have 12 atoms in the 12 corners. Right? Okay. And you have 2 atoms in the faces on the top and in the bottom. Right? 2 atoms. And you have 3 atoms inside this unique cell. And this is what we call unique cell of the crystal, hexagonal close-packed crystal. So the top and the bottom faces of the unique cell consists of the 6 atoms, right? 6 atoms that form regular hexagonals and surrounding a single atoms in the center. Okay, in the center. These single atoms in the center. And another plan, this is another plan, right? If you think this is layer 1, layer 2, layer 3, or you call plan A, or plan 1, plan 2, plan 3. Another plan that provides 3 additional atoms to the unit cell is situated between the top and the bottom planes. Top and bottom planes. Between the top and bottom planes, which is this one. So unit cell of the HCP, okay, the equivalent of the 6 atoms is contained in each unit cell. So for example, you have 1/6 of the atoms in the corners, and you have 12 atoms, right? So 1/6 times 12, that means what? That means 2, equal to 2. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. This is 1. Okay, and you have 2, half of these atoms in this unit cell, and half of this. So that means what? Half times 2 means equal to 1. So you have 2, 1. And how many atoms here? It's all inside this unit cell. So there are 3. So 1, 2. And then that means then you have 3, 1, 2, 3 here. It's all inside these atoms. These 3 atoms are all inside this unit cell. That means 1 times 3 is equal to 1. So how many atoms here? There are 6 atoms. How about the coordination number? If you take a look of this one, so there are 6 here, right? And then above the layer of this layer, this plan is there are 3 here. And below there are another 3. So that means coordination number will be what? Coordination number will be 12. Right? Excuse me. How about APF? APF is a little bit comprehensive to calculate. I just directly tell you the answer is 0.74. 74%. Actually, this is you might say, wow, Professor, this is the same percentage as the percentage of the FCC. That's correct. That's correct. Because the only difference between FCC and HCP is the packing sequences. Packing sequences. and nothing more, nothing more. So for the HCP is metal, for FCP metals, including these types like titanium, zinc, magnesium, cadmium, cadmium. Okay. So HCP, that will be the layer, the group 2, group 3, group 4, group 7, group 8. As you can see here, this is HCP, 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 HCP. You don't need to remember this very well. Once you need this information, you just Google it and you just find this table, I think, in the internet. So that won't be any problem for you to find out which element belong to what type of the crystal structure. So what I want to tell you here is that, you know, the APF is 0.74, which is the same as HCP, and the only difference is the packing sequences. Only difference of this structure is the packing sequences. So for the two-dimensional projection, as I say this to you, this is bottom layer, A site. And for A site, after that, you have choice of B site and C site. You put the B site first. Oh, so this is the middle layer, which is the B sites. And then next, you can put the atoms in the A site, or you can put the atoms in the C site. For the FCC, that will be for the FCC structure, that will be ABC packing phase sequences. For the HCP, that will be AB sequences. So in this case, A site, B site, and then after that, you will put the atoms in the A site. So this is what we call hexagonal close pack structure. So AB packing sequences. Right. So just let you know the comparison of the packing sequences here. For FCC is ABC, 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 ABC. For HCP is AB, AB, AB. It looks it's very similar, right? Okay, that's why the APF is exactly the same, 0.74. Right, here I just want to give you some information. I just summarized the information for you here. We learned 4 crystal structures of the metals. And for the atoms in the unit cell, there are 1, 4, 2, 6 for single cubic, phase cubic, and body cubic, and hexagonal close packed. Coordination number is 6, 12, 8, 12. I'm sure you know this already. For APF, 0.52, 0.74, 0.68, 0.724. And for elements here. And you need to know the relationship between the radius and the H length. Okay. For your information here. So let's move to the section 3.5. We call density computations. Density computation. You know how to measure the density, right, of a substance or of a material. That means what? The weight divided by volume of this material. How about theoretical density? You don't need to measure, you just calculate. This is called theoretical density. So you need to know the definition of the theoretical density. Of course, the density will be equal to weight divided by volume, right? And then how do you know the volume here for this? You do the theoretical density start from the unit cell, because the unit cell is the minimum, the smallest volume, and you can repeat in 3 dimensions. So this, you can calculate this density for this unit cell, and then that will be, this density will represent the density of the bulk material. Okay, so, and first of all, you need to know how many atoms in this unit cell. For example, in the case of BCC, that will be 2, right? So this is how many atoms in this unit cell. And of course, you need to know the volume, and it's easy for you to calculate the value because if you know the length of the edge, or we call edge length, and you times 3 times of the edge of length, you got this value. Okay, but if I don't tell you the edge of this length, the edge length of this unit cell, I tell you the radius of the sphere. Can you calculate that for me? Yes, you know, right? Because you know the relationship between the radius and the edge length. Okay, and how about this one? What is A? A is atomic weight. The definition of atomic weight is how many grams per mole, right? It's how many grams per mole. So, and then what is N? N is Avogadro number, which is 1 mole. So if you know the numbers of the atoms in 1 mole, and you use this atomic weight divided by Avogadro number, that means what? You know, if you divide, you know how many grams per atom, right? You know how many grams per atom, because this divided by this, then gram per atom. We know this when you are in first year, right? And then if you know how many grams per atom, and you know how many atoms in this unit cell, so you know the weight of this unit cell. You know the weight of these atoms in this unit cell. So ladies and gentlemen, I want you to remember this equation very, very well, because actually this is not difficult at all, right? Okay. This will be in your final exam. Definitely. 100%. And now you wake up, right? Now you start to get excited to learn. Okay, here I give you an example. So this is theoretical density I just show you here. So just here I give you an example. In your final exam, I tell you that, well, please calculate the theoretical density of chromium. And chromium is the crystal structure of the chromium is BCC. I just tell you this information. Okay, and then I will tell you that, well, the atomic weight of the chromium is 52 grams per mole. And radius of the chromium is 0.125 nanometer. You will say, wow, Professor, how nice. I just put this information in this equation and I got an answer. That's right. That's right. So it's very easy. And I still found some of you cannot get an answer. I don't know why. Anyway, I saw you are top 15% in this country. You are top 15% of the students in this country. Okay, so don't let me down. Even this simple calculation, you cannot get an answer. I feel disappointed. You are top 15%, okay? So the only thing you need to, I don't want to tell you is this one. If you don't know that number n is equal to 2 for BCC, that will be the end of story. You don't know how to do the calculation. Okay, and I don't tell you this information. You need to do this for me. You need to know the relationship between the edge length and the radius. And of course, this is easy. And so you can put this all the information in this equation. As a result, you got an answer of 7.8 or 7.18 grams for cubic meter. 7.18 gram per cubic meter. So this is called theoretical density of the chromium. So you can do the same thing for the copper. You can do the calculation. You can do the theoretical density of the copper. You can do the theoretical density of the silver, gold, whatever. As long as you know the wave, as long as you know the atomic weight and the radius and the crystal structure. Okay, but when you do the calculation, when you can do the calculation for the cylindrical density, you can also do the measurement of the density for the density of the chromium, right? For the actual density, it's about 7.19 grams per cubic meter, which is quite close. And you know why? You might ask me, Professor, why? Wow, there are many. We will talk about the defects in the chapter 4. There are some imperfections and impurities, always. So there's nothing perfect. We are doing the perfect things. Theoretical means that it's always perfect, right? So actually, in this world, there's nothing perfect. You always have some impurity or imperfections. Right. Another example in your textbook is in example 3.3. Okay. So here is that I give you the information of the radius of the copper, and I give you the atomic weight of the copper, and I give you the types of the packing. And I want you to do the calculation. I want you to find out the cylindrical density. Easy. Piece of cake. Right, so if you compare the densities of the material classes, we know that metal is the heaviest compared to the ceramic, compared to the polymer. Polymer is plastic, always light. Always, the weight is always light, right? Why? So for the metal alloy, they are always heavy. This is the y-axis is density. Okay, and this metals alloy here, and the graphite, ceramic, semiconductor, and this is ceramic. And the polymer is the density is lowest. So as you can see, that metal, the density can reach to about 20 grams per cubic meter. Okay, and then ceramic can be in the range of 5, 6 to 1, something like this. But for the polymer, it's always 2, 1, or even 0 less than 1, lighter than water. For composite, it's between the ceramic and polymer normally. So why? There are two factors. The first factor is that because metal has a closed packing, they pack very well compared to ceramic, compared to polymer. Another reason is the metal always heavy. Weight, weight per volume, right? So if you are packing very well, and then the metal, the weight is heavy, so after you calculate, the density is high. And for the ceramics, has less dense packing and the lighter elements, right? So for example, silicon dioxide, you have oxygen, right? Silicon nitride, you have nitrogen. So you have these light elements, of course, the density will be low. And polymer normally is not packing very well. It's not crystal. So you have many spaces in this material. So if you have many spaces, of course, the density will be very small. Okay, so low packing density, often amorphous. Amorphous means what? Can you tell me another name of the amorphous? Does anybody want to tell me another name of the amorphous? 0.5 points. That will be the lecture in last week. Another name, what you can call amorphous? Yes. Anybody? 0.5. That means you, yes, please. Thank you. Thank you very much. Non-crystal, right? Good. I'm very happy for you. Good. Amorphous. is equal to non-crystal. Okay, that means it doesn't pack very well. Crystal, non-crystal, and crystal, non-crystal can be referred to amorphous. Okay, lighter elements, carbon, hydrogen, oxygen. Okay, the composite between, composite is composed of the ceramic and polymer. As well, the density is always between the density of the ceramic and the density of the polymer. Right, okay, show you here. So you have, so as here just show you some of the information. Titanium here, platinum, right? Platinum, and then gold is all very heavy metal. And silver, titanium, right? And then silver, tungsten, okay? And the copper is all, it's all heavy metal here. Okay. So again, this information is telling you, this information telling you the density periodical table at room temperature. The one here, is the density is very high. Density is here, showing you. Yeah. Okay. Right. So here I just want to tell you the comparison of the atomic packing factor. You might say, well, what's the difference between atomic packing factor and the theoretical density? Easy. APF is volume per volume. That means what? It's a dimensionless quantity. So it's just talking about the ratio of the value of the sphere and also the value of the cube. But for the density, it's weight per volume. As you can see, here is the same volume, right? But only difference is the with APF talking about the volume, density talking about the weight. Right. So for ceramic, crystallized ceramic and polymers, we don't talk about this here because it's a little bit complicated. More complex than BCC and FCC. But we will have something related to this very soon. So density and atomic packing factor of these materials are used modified forms of the equation. So for the 3.6 polymer, do we have? Let me see that polymorphism. Right. So section 3.6, we are talking about, can we change the structure of this material when we change the temperature? Or can we have two different structures of this material at the same temperature, for example? This is what we call polymorphism, or we call allotropy. Okay, allotropy, polymorphism. So what is polymorphism? Polymorphism is that some metals and non-metals may have more than one crystal structures, a phenomenon known as a polymorphism. So you have two structures, or even 3, 4. The condition is often termed allotropy. These two words tell you the same thing. In the element studies, for example, carbon. This carbon is one type of element. So you can have many, many types of the structure. Graphite, right? Graphite is sp2. And diamond is what? sp3. Okay, but you can find graphite at room temperature. If you have a pencil, the graphite is there, and you can find a diamond in jewelry shop. Okay, but these two is different structure. These two are different structures. So for iron at the room temperature is BCC. But if you increase the temperature up to 912 Celsius. And the structure changed from BCC to FCC. Okay, this is because the temperature change and then atom move. The structure change. So from BCC and to become what? FCC. So you can play the structures by temperature of the okay. So these are the example. So for iron, carbon is diamond and graphite. You have, this is sp3 structures, and this is sp2 structures. Okay, for the iron, BCC at below 112 Celsius, we call alpha iron, and between 1394 and 912, we call gamma iron, and above there's another structure we call delta iron. Okay, and this case is TIM. The TIM is that at room temperature like 25 Celsius, the structure of the TIM is we call beta TIM. We call white TIM, and structure the unit cell looks like this. But if you reduce the temperature below 13.2 Celsius, we call cooling. The structure changed to this. We call gray TIM. From white TIM to become gray TIM. Okay. And the funny, interesting thing is that when you change the structure, the value change, the density change, I should say. The density, because the weight doesn't change, so the value change. So the density change from 3.3, and this is called metallic bond. Metallic bond. The bonding is metallic bond. Okay, and then when you drop the temperature below 13.2, density dropped from 7.3 to 5.7. And this is covalent bond. Covalent bond. And you can see it's sp3. So it's very interesting, right? The band gap change, and you can tune, Okay, and because the density reduced, so value increase. Value increase. So this is how it looks like. The white TIM to gray TIM's transformation. So this white TIM, of course, this represents two different temperatures, okay? So if you increase or decrease the temperature, it becomes gray TIM, and value change. And this shape deformed because value change. Okay? So I think there are some summaries here, and let's skip this. So the section 3.7 is crystal systems. As we know, this TIM, right? This is called body center hexagonal crystal structure. This is also the one type of the crystal structure. It can repeat in all directions, smallest repeated unit. Okay, and this is called body center cubic crystal structure. So how many crystal systems in the world? There are only 14. Okay, there are only 14 systems. If you find 15, the number 15, please come to me. Let's get Nobel Prize together. Okay, if you're really smart, good enough. Okay, there are only 14 systems, no more than this. Okay, so before we talk about that, let's think of the unit cell geometry first. So this is the unit cell geometry. Is that the crystal structure grouped by what? The unit cell configurations, the atomic arrangements. You have this unit cell. So you need to know where is the atoms in this unit cell. So we call this atomic arrangement. So, but before you put the atoms in this unit cell, you need to know the definition of this unit cell. For example, there are 6 lattice parameters. So one is A, B, C are the lengths of these materials. The length of this cube, right? Alpha, beta, gamma is the angle of this in this unit cell. So x-axis and y-axis and z-axis And the edge length parallel to x-axis is called A. And the edge length parallel to the y-axis is called B. The edge length parallel to the z-axis is called C. Okay? So you need to know this definition before you have addressed any spheres or any points in a space in this unit cell. And then you have alpha. Alpha is the angle in the YZ plane. And you can address this is in the x-axis, and next is the alpha is YZ plane, the angle. And then beta is in the, beta is to the y-axis, right? So it's in the XZ plane. There's a mosquito. Okay. Sorry. Okay, and then what? And the gamma is, related to the z-axis is in the XY plane. Okay, so I hope you still remember we're talking about crystal lattices. Lattice is the, you need to know that these words, okay? But before that, let's have the definition of unit cell. As I just told you, unit cell is the smallest repetitive volume, okay, which contains the complete lattice patterns of a crystal. This is the definition of a unit cell. And for crystal lattices is this, you have 7 crystal systems, or we call 7 crystal classes. That means you can have 7 crystal systems, and you have 4 lattice type. 4 lattice type means that you put the atoms in this crystal system, and we call crystal structure, right? So in total, there are 14 crystal lattices. That's why I told you only 14. So there are 7 crystal systems. We just talk about cubic structure, right? But actually, there are another type of crystal structure, and you already learned it's called cubic crystal structure and hexagonal crystal structure. But there are another few types, such as tetragonal crystal structure, and also rhombic crystal structure, and monolithic, monoclinic crystal structure, and then rhomblohedral crystal structure, and triclinic crystal structure. I don't need you to remember all of this, but you just need to know roughly there are 7 crystal systems here. And now it's time to put the atoms in these 7 crystal structures, right? So as you know, there are 7 crystal classes, and then if you put the atoms into this in a triclinic, in the 8 corners, this is called symbol cube structure, right? So if you put the atoms in this, there are 1, 2, 3, 4, 5, 6, 7. And for the volume centered, you can also call body center. Body center is also called body center, value center. You put another one in the center. There are only 2 types, 1, 2, 3, 4. And base center is rare. Rare is you put the 2 atoms in the top face and then 1 bottom face. And the face center cubic crystal structure is you put 8 atoms in the 8 corner and you put 6 atoms in the 6 phases. It's called FCC, right? There are only 2, 1, 2. Again, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are only 14 structures in the world. Okay, so that's what we call 14 crystal lattices. We call Bravais lattices. Okay, tell me which structure belong to this. This is silicon, right? sp3, and this you can, if you replace silicon to carbon, this is structure of the carbon. Is this unique cell? And which Bravais lattice? This structure belong to which Bravais lattice? Tell me. You might say, "Wow, Professor, I got number 15 crystal structure. Let's get Nobel Prize together." But is this which one? Which Bravais lattice belong to this structure? Can you tell me? No, you cannot. No, there's no one you can find out is this type of structure, right? So this tell you what, this is not a unique this is not a unique cell. And this, how can we find the unique cell of this carbon, diamond, or silicon crystal? Okay, and that's what I'm going to tell you, the crystal structure of the metal, ceramic, and polymers. So actually, crystal structure is a combination of, this structure is a combination of 2 factors. Okay, for example, this crystal structure is a complete description of atomic system. Okay, so this complete description of atomic system like this. So there are 2 factors determine this crystal structure. The first one is Bravais lattice. There are 14 Bravais lattice, or co-crystal lattice. So for example, we call the point environment. Point environment, a set of the points space in, there are only 14 types. That's why the table we just showed you in the previous page. Plus what? For example, FCC, BCC, FC, something like this. Plus what? Plus a basis. You need to know what is the basis. The basis can be 1 atom, can be a pair of atoms, can be a molecular, that means composed of many atoms, like for example 4 atoms. So this is called basis. So the group, atom group in each lattice. For example, I want to tell you is that this one, you can put 1 atoms in this location. You can put 1 pair of atoms in this position. You can put 4 atoms which are molecular in this position. Okay, and this is called basis. So if I give you a structure, you need to find out the crystal structure, depending on 2 factors. One is you need to find out what's the basis of this crystal structure, and after that is what's the Bravais lattice in this crystal structure. Okay, so for example, this atomic group, this one can be a copper atom, can be a methane molecular, it can be a sodium chloride ion, sodium chloride material molecular. Okay, so here I want to show you is that the Bravais lattice basis, for example, and this is a crystal structure. So for the FCC, is if you have an atom, and this example here is you have a gold, aluminum, copper, platinum. This is FCC. If you put atom here, right, and this is FCC of the crystal structure of the gold, right? This can be aluminum, this can be copper, this can be platinum. And we know this, we learned this today. Okay? And then how about if you put a molecular in this position? For example, methane. And this is called methane ice. Methane is in the form of gas, right? But see, if you reduce the temperature low enough, methane will become a solid. We call methane ice. Bounded by what? Chemical bond or physical bond? Methane ice, that means methane molecule put together very close. The bonding between two methane molecules is called secondary bond, right? Secondary bond. And the interaction is induced dipole, or London dispersion force. London dispersion force, right? I should give this question in Kahoot. Okay, I hope you still remember this. Right. So this also crystal structure also called FCC. And if you have an ion pair here, ion pair means what? Means sodium chloride. Sodium cation and the chlorine anion. If you put this sodium chloride in the pair, also is FCC. So we call this rock salt crystal structure. Another name, but actually it also belongs to FCC. It's just the position from one atom replaces two atoms, one pair of the ion. Okay. How about atom pair? Atom pair, for example, carbon with carbon, these two carbons, and with a degree of 109 degree. This is, you put one here and then degree of 109, or you can here, and this is called what? You can use it can be silicon, it can be carbon. This is what we call what? Diamond structure. Diamond structure. So diamonds also belong to face center cubic structure, but with a basis of the atom pair. Okay. So let me show you an example here. Is that, this FCC crystal structure, as you can see, the 5, 1, 2, 3, 4, 5 in the first layer, 4 in the second layer, and 5 in the third layer, right? 5, 4, 5 here, right? Okay. And then if you replace the copper to carbon dioxide, that means what? Carbon dioxide is what? Carbon dioxide ice is what we call in Chinese ganbin, right? Ganbin. Okay, so if you put the carbon dioxide molecules in this position to replace copper, this is also FCC 545. Carbon dioxide ice. Carbon dioxide ice is a crystal structure. Okay, how about rock salt? Rock salt is like this. You have the chlorine anion here, 5, 4, 1, 2, 3, 4, right? Oh, sorry, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? This chlorine anion, sodium anion, sodium cation, 4, 5, 4. So it's one is 5, 4, 5. One is 4, 5, 4. And this is rock salt. This is not unit cell. This is not. Because this, you can regard this as a pair. That means what? That means this is a pair. So this represent one position here. And another one on the top, another pair here. Or of course I don't show you here, right? So it represents this position. Okay? And how about this one? This pair is represent this one. This one represent this one, right? How about this one? This pair represent this point. Again, this one, there's one missing here, right? This pair represent this point. Are you with me so far? No problem, right? Good. Top 2%, top 15% students. Good. So this is the crystal structure. This is the unique cell of the diamond. Okay. So this is unique cell of the diamond. It looks like this and repeat. So this is not a unique cell. This is the unique cell of the diamond and silicon. So once you want to calculate the spherical density, you don't use this, you use this. Okay, there's some information for you to digest. You know, when you know the structure name we call rock salt. There are many names of the structures in ceramic, like rock salt, cesium chloride, zinc blende, and fluoride. And I'm sure you know this. It's called perovskite. You know the solar panel, solar cell. Now we use most of the structure of the structure. The material we use for the solar cell nowadays, very high tech, is perovskite structure, a spin nail structure. You call ABX3. ABX3 means that you have this AB represent cation. Okay, you have cation and ion, and there are some of the example here showing you here. But it's a little bit complicated, so we don't have time to talk about this in this class. Right. So for the wallpaper, you know, when you're at home and when you go to some places, you have wallpaper on the wall. So it's a kind of odor, and it's also two-dimensional crystal structure, and has to form it's always from the 14 Bravais status. So this wallpaper, again, I want you to find out where, can you find out for me where is the unit cell? And what is the repeat unit? What is the basis? So you need to tell me where is the unit cell and the basis. What is the basis? Okay. So just give you an example. You know, you put dozai together, right? Sorry about this. Okay, this is a unit cell. Sorry to very happy to please you. Everybody get up, right? Okay, so this is Rhomber's crystal structure, a unit cell, and tell me the basis. Basis, you know, again, the basis also need to be repeated. Okay, this is basis. This is the basis. You know, I'm sorry, you need to extend this a bit more, and you know this is the repeated unit. Okay, this is the basis. And for this point, this is repeated unit. This point, this is repeated unit. Of course, this point, this is repeated unit, right? The same as this. And again, this is repeated unit. You can tell me, anyway, you might not happy say, Professor, can I use repeated unit from here? Yes, you can. And repeated unit from here? Yes, as long as you can repeat. So there are two informations you need to digest. One is unit cell, one is basis, right? Right, so Bravais lattice, this is the great man. He found out this mathematical proof that there are 14 distinct ways to arrange the points in a space. Right, so this is the summary. Right, you know, this guy find out, wow, pentagonal can make a crystal. And then he got Nobel Prize in 2011. And this is real. This is rare because this kind of crystal is not easy to find. But he's the one who found this. He made this become crystal. Okay. Right. So that's it today, and I hope you enjoy the lecture today. And I will see you next week.